Thank you. So thank you to the organizers and so on for organizing this workshop. So I'm going to give a whiteboard talk, and I hope to be as okay, thank you. And I hope to be as pedagogical as possible. It will be a very non-historically correct introduction to DFT, in the sense this is not how it was thought about originally. How it was thought about originally was in terms of a truncation of closed-string field theory, and then it evolved in various ways. But I don't want to give that point of view. I want to give a much more mundane point of view and show you how this can lead to some intuition that we can use to extend it in various directions. So this will be sort of a non-historic intro to DFT. And the basic idea that I'm going to use, and the intuition that I'm going to try and use, is that of Kaluza-Klein theory. So I'm actually going to start with Kaluza-Klein theory and tell you loads of things that you know, with the point of view that that will give us a way to generalize and extend, and where we have to do something different to ordinary geometry. So let's begin. We have 4D Einstein-Maxwell. So I have the fields of the metric of a one form, and we've got the usual action. I'm going to be in 5 dimensions. And this is something we all know and love. And crucially, we know that the local symmetries are given by diffeos, which are generated by some vector field and gauge transformations of A. So delta A mu is, is d mu chi. And we have these two local symmetries. Now, what Kaluza and Klein then wanted to do was say, how do we then combine the fields in the theory, G and A, to form one single geometric object, and at the same time combine the local symmetries to also produce one single symmetry. And of course, the answer that we know is that we combine all of these using 5D gravity. So we have the combination of coordinates that eventually will allow us to combine this vector with this gauge parameter into one thing. And then, of course, the thing we know and love is and I'm going to not talk about the scalar field here. We all know it's there, but let me skirt over that and we'll discuss it later. And crucially, it's the fact that the 5D diffs now, as generated by the Lie derivative, combine so that we then have some 5D vector field, or in this case, covector field, which combines the vector fields that generated the diffs in 4D with the gauge parameter into a single 5D vector. Okay? And then we have the single 5D action and then we ask ourselves, how is this 5D action related to the 4D action? and how are these 5D diffeomorphisms related to the 4D diffeomorphisms and gauge transformations? And the answer is that if we insist on a constraint such that any field, in this case it would be the metric, must be independent of the fifth direction, then we reproduce the 4D action, and we reproduce 4D diffs plus gauge transformations. Okay? So this is something we all know. Okay. So from this perspective, I've not said why this constraint is here. I've said I'm doing it just in order to lift, and then once I've lifted to a 5-dimensional object, I ask myself what constraint will give me the 4-dimensional things. I've not mentioned low energy effective physics or any of those things, or quantum mechanics. That comes later. So once we've done this, this is all very well for Einstein-Maxwell with nothing there. We then ask ourselves, what are the electric charges? So the electric charges, Q, you can see, are going to be given by P5, the momentum in the fifth direction. So there's two ways to see this. One, you can put a probe particle in this background and then look at the geodesics and then see that if it has momentum in P5, then it will behave as if it's got electric charge. Or you can make a genuine 5-dimensional solution that has ADM momentum in the fifth direction and then see that that will also give you electric charge. Okay, so we discovered then the electric charges are given by this momentum. And then we can also see that we could look at charges that are, momenta which are null. So then we can consider null states, which would then have P5 equals P0, and this will then imply that Q is equal to M, and this will be our BPS states. Okay? So that was one way in which we get the BPS states, is that they're just null waves in the 5-dimensional space. Okay? Now, at this point, P5 can still be anything, because I've not specified anything about the topology or any global data on the fifth direction. If I wish to have charge quantization, then charge quantization will imply, well, that you periodically identify X5. Okay? And then that will give you charge quantization. Yes, Martin. Yes. I didn't say why. Yeah. I didn't say why. I've got to say why. Why is this?
No. But independent of that, you still have that integral.
Yeah. That's right. That's exactly right. I've not discussed it. But now that I've come down to here, well, okay. Now that I've got this conclusion, then I can go back and discuss it, and then I get a finite number, and it's fine. Okay. So so this is all very well, but now we could do one more thing, which I want to discuss, which actually came significantly later. I mean, most of all this was done in the 1920s, and so on. But then later you could ask, where are magnetic charges? And this is where something a little bit more interesting happens. So So let's say the conclusion by the time we got to here was that our 5-manifold was M4 cross S1 of some radius r. And then you go and you ask instead now for magnetic charges. QM. And then you realize that the resolution to that is that you require that this is only locally true in a patch, and that you require the S1 to fiber non-trivially, so that what one does is one writes the M4 as being, you take out time, you go to polar coordinates, cross S2, and then instead of having S1 cross M4, we now construct, let's say for a single magnetic charge, the Hopf vibration of S1 over this S2, and then this will give us the so-called Kaluza-Klein magnetic monopole of, and I think it's Perry, Gross, I guess that should be the order, and one other, Sorkin, thank you. Sorkin, okay. And in fact, it's interesting to me at least how this happened some, almost 50 years after, maybe more, even though we knew from Dirac's work that what we needed to do was do a fibration. Okay, so now we also have a construction of how we get the magnetic charges. Okay, now, the next step that people did was that, of course, you can consider even higher dimensions, and instead of doing an ordinary reduction, you can do so-called Schwarz reductions, and so you can reduce on something like a group manifold, and then we can obtain things which are not just abelian fields, but non-abelian fields. I won't write that out. People are familiar with that. But the next step is then, indeed, instead of having an S1, have some Schwarz reduction, and then get some non-abelian fields. Okay, so all of this was predicated. Fine.
Well before Yang and Mills.
Well, even better, even better, even better. So Yang and Mills they were predated by doing this geometric construction. I like that, that's good.
Yeah.
So now all this was predicated on saying that what we wanted to do, let's write it up here again, was combine two fields into one geometric object, the metric and the one-form, and crucially combine the local symmetries of diffs and one-form gaze transformations, and realize that that could be made into 5-dimensional diffeomorphisms. So now we're going to take a step back, and we're going to go back to the NS sector of supergravity. So I've already heard today that people are making theological declarations about who is their God. So we've got now the very well-known thing of, and I'm omitting dilettantes, but okay. And there can be fermions and other things, but the thing that you want to ask yourself, you have a field, G mu nu, and now a two-form B mu nu. And of course we have, let's say I'm in D dimensions, we've got D-dimensional diffs. D will perhaps be 10, but whatever. Diffeos, and now we've got the variation of B. Being given by a one-form worth of gauge transformations. And now, of course, one could have looked at this way back, maybe people did, and said, I want to find a Kaluza-Klein lift of this theory. I want to combine G and B into one object and give it a geometric interpretation and write down a single action for that combined object. And then, crucial to that, I will want to have something like a Lie derivative generated by some generalized vector field that will generate for me diffeos and B-form gauge transformations. Okay? So that would be something that you could think about doing. Okay? So if you try and do that, let's see what happens. I mean, it's useful to do on. So the first thing is, how many dimensions do I need to lift? Okay. So with Kaluza-Klein, I just needed one dimension. And that was very much tied up to the fact the local symmetries that we're going to have give me a vector field, one sec, just required one extra parameter, which is the gauge transformation. Here, I have a one form's worth. So if I want to make this, both of these things generated, so I've got here V, and I've got here nu, then I will want to have some extended space with a vector field that will be given by, let me write it, call it something else, nu, that will be given, that will have twice the dimension. Yes, Jack.
I would have subtracted one because the chi's also have...
Reducibility will come to. We'll come to reducibility later. Okay, that will be, that was just a crucial part of the story, but let's not jump the gun. So at least, I mean, you've got this as the transformation, and then the reducibility's got to come into the geometry later. So the first statement is, if you're going to have a generalized vector field that will generate the Lie derivative, you must now have 2D dimensions. That's just counting. And the next thing you do is you say, well, how do I combine G and B? Well, you sort of look at this thing, and you go, well, I can construct a metric and then I need something down here, and I just write the answer. And this is, apart from this block at the bottom, this is exactly what you would do if you had D vector fields in Kaluza-Klein theory. Okay? And then I'm fixing this, and I'm going to tell you how I fix this bottom part in a second. But you can see from this, it's effectively the same thing as Kaluza-Klein, but you've got D copies of vector fields. Okay? So you have this, and then you think, well, this is a good guess. And you then take this thing, and then you calculate the, is that two? And then you calculate the Ricci scalar of this object subject to the constraint that, let me call dx tilde equals 0. And just so we're clear here, if I'm extending the vector fields, the idea is you're actually going to add dimensions. So I will have an xi, which will have an x and an x tilde. Okay? Right. And then, just as we did in Kaluza-Klein, just one sec, you say, I won't depend on that and see what happens, subject to later making the thing finite and so on. Okay. Neil.
Why do you think the x is that? I know that this figure tells you.
So this is the starting point, is that B must be antisymmetric. So I'm trying to reproduce this thing. That's the starting point. If you want to tell me, just don't do that at all, then that's a different game. I'm saying, this is my starting point. Lift this, a la Kaluza-Klein. Yeah, Mark.
Sorry, what's the topology of this two-dimensional thing?
Don't ask the hard questions now. Ask the hard questions later. We'll come to that. I'm going to build this up slowly. We're going to get somewhere, honestly. Yeah, absolutely. But you know what? This has actually got det 1. But okay, that's one of the little tricks. That's one of the ways one of the ways. And when you do ordinary Kaluza-Klein, you actually do some choices to make the determinant factors easy as well. Well, no. Let me go one at a time. We can include the dilaton and we can do all that, but let's do one thing at a time. So this is what you would guess based on Kaluza-Klein theory, and I suspect people even did try this, because then what happens is you get junk. And the reason why you get junk is something that you know straight away, because this is just the Kaluza-Klein ansatz, all right, with some special choice of the internal space. But the crucial point is you do not recover the appropriate gauge symmetry, or if you like, the gauge invariant thing for B, because it's like having D vector fields, and thus you would have, when you did this reduction, you would actually land up with the right Einstein-Hilbert, but then you would have and then I'm going to put a row here, where the idea is that you're summing over row, but there's no sense in which you're anti-symmetrizing over row. Okay? And that's just from doing D types of Kaluza-Klein. And this, of course, does not have the gauge symmetry that you want, because the gauge symmetry comes from the fact that H is equal to dB, and I have total anti-symmetry. So then I think at that point, people gave up and said there is no natural lift a la Kaluza-Klein in this way. So you can persevere and say, okay, it doesn't work for our usual notion of geometry, but instead, what we're told is that, and you've got to instead generalize our notion of geometry, so that then we will reproduce the appropriate actions and gauge symmetries. Okay? So how do we do that? So this is where we've just got the usual Einstein-Hilbert in 2D. So instead, what you can do is just guess, meaning write out an arbitrary two-derivative action in G inverse and G, where you contract all the indices that you can contract with two derivatives. Okay? So here, you'd have terms like, I don't know, IJ, IJ, LK, LK, and then there's actually another 5 terms, given from just working out the different ways that you can contract that, and say, and then demand under this x tilde thing equal to 0 that you do recover Einstein-Hilbert plus h. And then ask yourself, are there coefficients, so there'll be a coefficient, let me say this is A1, A2 will be another one. Are there a set of coefficients where that will be possible?
Still, before you start this, you have to specify G element.
This G, you mean?
No, the lower block there.
Yeah. So I'm going to take this as my given generalized metric
Lower block.
with this lower block, which is the inverse.
Just the inverse.
Yep. I mean, there are other reasons to do it. I mean, I'm using the word generalized geometry meaningfully in the sense that this was what Hitchin came up with. So you say, in other ways, Hitchin's told you there's a notion of a generalized metric. Can you make an action with it? Okay. Yeah, but we can, all of us now think of more efficient ways to do this calculation, but we do this, and then we then come up with the set AI of coefficients such that when we do this reduction, we end up with Einstein-Hilbert plus h squared, meaning back to our usual NS sector. And so you think, okay, we've done something useful, perhaps, but then we need to explore it some more. So what have we actually done that has allowed, I mean, because this is not the Einstein-Hilbert thing, so what are you doing geometrically? I've just given you an action with some arbitrary coefficients, and I've not told you actually, and this is one of the clues, is going back to what really is the notion of the generalized Lie derivative, okay? So, so I go back, and then I say, right, I will, yeah, go on.
We know sometimes you go to kilobytes.
Yeah. There is a Berman version of this in the same way. I mean, it's, you know, yeah. Yeah, sure.
There you are using the regular partial.
Yes, I am.
If you use covariant,
yes. Right, so very good question, which is related to the next thing I'm going to say. Normally, when we construct an action in GR, we use covariant derivatives, and the reason why we do that is because we want the thing in the end to be generally covariant under local gauge transformations, under local transformations. Now here, I've not told you yet what the local transformations are. So now I'm going to tell you what the local transformations are, and then the next thing to check is that this action will also be invariant under those local transformations, but it is not manifestly so at this point because of partial derivatives. Okay? No, but it depends how you write it. I can write it as the commutator of covariant derivatives, or I can write it just all out. Yeah. Yeah. Fine. Yeah. Yeah. So what we do is now we say, what is the generalized Lie derivative? So we have something that we will want to act on this generalized metric and create the transformations well, let me not do it on the metric at first. We can just do it on an arbitrary vector and then infer what that is for the metric. So in fact, let me not get my notation confused. I'll call that U and that V. And then we're going to say it's going to be like the usual derivative, Lie derivative, but we will allow ourselves a deformation, which I'll control with something called the Y tensor. L. So if the Y tensor is 0, then this is just the ordinary Lie derivative. And if not, then we've changed it by this thing. And we do this because with Y, so Y should be an invariant tensor of the theory. That's crucial. And it should be globally defined. This is where we start now with the notion of a global structure, because I require this thing to be a globally defined invariant of the theory. And then we find that Y is actually given by the existence of a single tensor, eta, and this is the inverse of eta, which is fine, which is the ODD tensor on the 2D dimensional space. Okay? So in other words, we now have a space with an ODD structure, and we insist our local transformations, so what's not obvious, but you can show, this generalized Lie derivative preserve the ODD structure. So it's not ordinary Riemannian geometry, you're saying I've got geometry that preserves an ODD structure. Yeah.
Your definition,
Yeah.
put it in brackets. The derivative, does it act?
This derivative just is like that. And V, no, this is correct, yeah. L, contract with this L. I is up here, so this will have an I. Yeah, this is correct. Okay. So, so now we've got what the infinitesimal transformations are, as generated by some generalized vector field. And then what you check is that if you act on the generalized metric, via this generalized diffeomorphism, you reproduce d-dimensional diffeos and the correct two-form gauge transformations. Not yet. Related. Everyone knows lots of words to say to me, but we're going to get there. So at the moment, this is related to it. You need to anti-symmetrize it to get the door. Oh, okay, yeah. Right. So now we've got this. The next step you would do, yes, I check that this action is invariant under it, is you then ask yourself if this closes. Okay? So I say, so I've constructed a theory, I've got a local symmetry, I've got some sort of geometry in the sense I'm doing coordinate transformations that preserve eta. And now I ask myself, is this true? Where now I need, and this would now be what's called the C bracket. And what I find is it's not true. So it's not closing. And so I would start to worry. But then it closes up to the existence of terms that look like this. And I'd have to think what goes in here, but there's a whole bunch of mess, but it closes up to the existence of these sorts of terms. So then what you say is that in order for this thing to close, we impose the constraint acting on all fields equals 0. Okay? Now, of course, this is solved by dx tilde mu acting on anything is equal to 0, which is how we constructed the theory. But it already has something a little bit more general, which is that we can consider different solutions of that constraint and see what you get. So, but maybe I'll come back to that in a second. Okay? So now we have, and I should say this is where we now get a sort of algebraic type structure because you can look at Jacobi and so on, and then link to Courant brackets, C brackets, etc. And we have things like that. Now, although this is solved by this, it's obviously also solved by dx equals 0. See, at the moment, I had no reason why I'm picking out x tilde versus x. So if I take this choice instead of that choice, you still get the same answer. You get also 10-dimensional, well, sorry, you still get the Einstein-Hilbert plus h. So that's just a result of the calculation. Okay, and then we'll come back to what that means later. Okay, now, but what I want to do next is follow the intuition from Kaluza-Klein theory. So now we've done what Kaluza and Klein did. We've got an action, we've got a local symmetry that's in a bigger thing. So then the next thing I want to do is find the electrically charged states. Okay? So what are the electrically charged states? Well, they'd be electrically charged states with respect to the H field. Okay? So this would be the charge of the F1 string. Okay? Because that would be the equivalence of a charged state. So now what we can do is, I wrote down the action, I could write some equations of motion, and I could solve the equations of motion looking, so find a solution to the equations of motion where I would have P x tilde mu to be non-trivial, where this momentum will be the equivalent of something like an ADM momentum defined in this space, which you'd have to do. And still have dx tilde equals 0. This would be like a plane wave, where the plane front would be along the x tilde direction. Okay, and null. So allow myself to have a 0. Okay. And then when you do that, it is in right. So I said there are two things that happen in Kaluza-Klein. To get an electric charge, I just need px tilde, and then I don't mention being null. But I pointed out that if it is null,
but when you said P5 is non-zero,
yeah.
then you no longer had P5 as 0.
Depended. Very important. This held me up for a while. There's two ways you see that five-dimensional Kaluza-Klein momentum is electric charge. You can do one with a probe particle, and then you don't have d5 equal. Then you don't have d5 equals 0. Your probe has got to go through, and we know that calculation. Or you construct a PP wave solution with P5 as defined by ADM equal to non-zero. The great thing, which surprised me, is that having an ADM momentum is still compatible with having a killing direction in that momentum. So if you actually just have a purely gravitational solution of a wave, then the wave does not have x dependence when it has momentum in that direction. Which is not obvious because that's what the opposite of the probe case. Okay? So we have P5, and then we have it null. The nullness is the thing which relates, makes the thing BPS, and then you can find such a solution. It's not any more difficult than the usual PP wave solution, and so then you end up with the charge of the string being equal to its tension, so which is what you expect from a fundamental string, and this choice of which x tilde did I have momentum in, it gives me how this string is aligned. Okay. So then I can then align it in the usual space by taking momentum along anywhere in the tilted space. Okay. So now that's cute, but then you should ask me, do I want the charge to be quantized again, and then worry about the finiteness of the action once I've integrated out things subject to the constraint. And so then this would imply that I will want to then identify x tilde with 2 pi r tilde. And this at this point is unspecified, but we'll come back to it. Now, once I've done the electric charges, you then say, can you do the magnetic charges? Okay. So now the magnetic charges, Qm, this will be the integral of H. Well, this will correspond to the NS fibrane. Guess it won't necessarily be a fibrane unless you're in 10, but the appropriate magnetic dual to the fundamental string in those dimensions. And then what you need to do is exactly the same thing as in the Kaluza-Klein monopole case, only now I'm solving this condition. There's no dependence on x tilde, and it's a circle, but now I can fiber it non-trivially around some S2 in the usual space. Okay. Now, the reason why I'm emphasizing this is that there is often a discussion, so when I wrote down this action, this is called double field theory, and there's often a discussion, how real are the extra coordinates in double field theory if nothing depends on them, right? I've got this thing and said nothing depends on it here. So I'll write a bit more about the magnetic charges, but if we, in order to have magnetic charges, we're requiring to have a non-trivial fibration, then that's saying you need those extra dimensions. Because without the extra dimensions, you can't fiber anything. There's no dependence. So the fibration will be trivial.
But this is really correct, because you don't have an S1 bound here, S1 reference, right? So, sorry, I don't want to mention that.
No.
So we have the generalized tangent bound, so what we really have is infinitesimal tangent directions, not the space-time aspect, and we glue the tangent directions together with the one lines. So
But that's all local. I'm actually going to give you something global now.
I mean, locally, this picture that I've generalized vectors,
Yeah.
but I glue them together, I switch it, products, right?
Yeah.
Generalized tangent bound.
Yeah.
But that's not an S1 vibration. Right?
So, all right. So we had this discussion in Durham as well. So I'm always, the easiest case, which I can just do and write down the solution and give you all the patching conditions, is if I've got if I've got an additional S1, then it basically becomes this, right? And then the H2, I can construct via the usual monopole construction. So so H3, which is your Dixon-Dowdy class, basically, if I'm on S1 cross M, then I can use the usual monopole construction for S2. But it does require the fact that the transverse space has got an initial S1. So that can be done explicitly. It's in my paper. Yes, Martin.
The other way of knowing, and we know the explicit, in the usual conventional language, we know the explicit solution to the NS5.
Yeah.
Right? And it is a Hoffman vibration.
Exactly.
And how does it fill it? But there
Yeah.
it's in terms of just ordinary force.
Yeah, that's right.
Of course, the fact that it's a T2 tells you it's involving the filament. How do you say it explicitly in this language?
Yeah, so explicitly what you would do, I don't think I've actually written out the metric here, but let me say, what you do, you're familiar with the Gross-Perry monopole, right, which is like Taubnut, effectively, with an extra fibration in R, and then instead of having the usual Gross-Perry monopole, where I take the S1 to be the space-time S1, I just pick a direction in the tilde and fiber that.
So you just take the usual
Take the usual Kaluza-Klein monopole, but then take the S1 fiber to be x tilde, and then when you read that off in usual space-time, that's the NS5. Yeah? Okay. And Mark.
Is there a reason why we're restricting to Schwarz vibrations for the
I thought it would get me into less trouble. And so, I thought, let's go into minimal trouble at this point. But I think we want to do it much more generally. But at the moment, let's sort of build up and then see what we can relax and the consequences of that. Okay. So here we've got this. So I'm going to say exactly this point, that we would have an S1 fibration over an S2, and the point is this will be in an X with X tilde. S2 will be the usual thing as I wrote before in terms of the transverse space to the fibrane. And this will produce, when you read off the space-time, this H, but what Kristin was warning me about is that I actually need an additional S1 transverse to the brane floating about. That's just technically needs to happen. I think the origin for this is that a lot of this has got hidden T-duality, and having that S1 in the transverse space effectively allows me to use T-dual constructions. But we can discuss it later, it's probably the best thing.
Explicit NS5 train doesn't have an extra.
No, it doesn't. No, it doesn't. No, it doesn't. So, absolutely. So I'm saying, I'm trying to be completely honest and say, where I have actually constructed the solution is in the case where I have an additional S1 in the transverse space, and then it is exactly the Kaluza-Klein monopole with this, and then it's just, that's what the calculation shows. And then Christian wants to say, if you did it in general, it's because you can't produce things which are really, because this is in H3 as a S1 fibration. It's essentially the statement that a general gerb is not an S1 fibration, which I agree with. I think that's your point. So I'm just saying that it's just the simple fact that H3 is equal to H2 cross H1 of S1 if I've got the S1 there, and then you can do it. So then that's allowing me to do it technically. Okay. And then the information of where the fibrane is oriented, again, is how you've picked which fibration, which direction that you're fibering. And you've got to do some dualizations, and then you work out which, where the fibrane world volume is oriented. Okay. Now, I want to make 2 comments. So, okay, so now we've got this magnetic charge. Yeah.
Technical question. Do you get the NS5 train or do you get the smeared?
This will be smeared. We can come back to how you remove the smearing. But to do that...
That's where the S1 comes from.
Yeah.
Smeared along that.
Yeah, exactly. You can do better, but that requires you to actually change this constraint. And I might discuss that later, depending on where we get to. So the next statement is that there's some sort of hint here, obviously of T-duality. We've got this ODD structure. We've got objects that are constructed that are, there's some sort of hint of that. So where is T-duality in double field theory? This is the next question. Because sometimes people say things which are not quite right. Sometimes people say, I've constructed a theory to make T-duality manifest, and so on and so forth. That's not what I would say. This is why I wanted to emphasize what we've done is that ODD is the local symmetry. T-duality is not a local symmetry. Okay. So what happens? So it works like this. So I've got this 2D dimensional space. And I've got this constraint which says, and this is what's called the strong constraint, that I really wish to remove the functional dependence of half of the coordinates. Okay? Subject to this eta tensor, which provides what's called a polarization. So what I need to do is effectively define an MD contained in this M2D, subject to this constraint, which means it's compatible with eta. Now, for an arbitrary d-dimensional manifold, then I will max out my constraint, and I will solve the constraint, and then I'll be forced to have a canonical choice of MD. If I depend on d coordinates in the generalized metric, those coordinates will be the coordinates of my manifold locally. Okay? So then I will end up with d-dimensional supergravity. There's no duality. But now, supposing I have some isometries. Okay? So really what this says here is out of these 2D dimensions, I've got d isometries inside those. But now supposing I've got more. Let's say I've got d plus 2 isometries. So let's just put some coordinates, just so I can write some things down, where I would have an x and a y in the usual space, and things depend on x, but they don't depend on y, and they don't depend on y tilde, which is the dual, and they don't depend on x tilde. Okay? But they do depend on x. So x is the coordinate that things depends on. Okay? Now, when I then have to specify what, yeah?
Do you really want the submanifold or do you want the quotient?
I love these sorts of questions. It may. I think I want a submanifold. Well, I know what you're asking. I know what you're asking. Because I've just effectively smeared, you're saying you were quotienting out. Because there's just no dependence on that. The way in which I would look at it, actually, this is a good question, is actually I think I do want a submanifold. And I'm going to tell you why later, but it's not within what I've written at this point. But I've got to tell you why. Okay? So let me just get to this point. So we've got everything depending on x. Nothing depends on x tilde, which would be fine. But now we've got nothing depends on y or y tilde. But I'm meant to pick a d-dimensional set. So I could have x and y, or I could have x and y tilde as the coordinates of my submanifold. Since nothing depends on y or y tilde, there's an ambiguity because I've got an isometry in picking what is the submanifold, which I call space-time. This goes by the name of physical section condition. Okay? So this choice is what's called a choice of section, and it's how we find the d-dimensional submanifold inside 2D. And there's only a choice if there's an isometry. When we take these two choices and then we apply of how we then read off what the space-time, the physical space-time metric is in its B field, that's T-duality. These different choices then give us the T-dual descriptions.
Technically, like you could do any rotation, so you probably want to say y and y tilde is on a torus, and then you want to restrict it with this speed.
Right, so then you've got to the fact that yes, to get the ODD Z, at the moment I've only got ODD. So to get the Z, you need to, yeah. Okay. So I want to emphasize this, is double field theory, before you have any isometries, does not have T-duality. But it does describe full 10-dimensional, in particular supergravity. But when there is an isometry, the ambiguity in the choice of section is what gives you the T-dual descriptions. Okay. Now, what this is very similar to is this is having the presence of this eta, which then gives you the polarization on the space, and then saying that I'm required to obey this constraint is very similar to what happens in geometric quantization. So this is something that you want to say, that you have x and x tilde is very similar to what you do in symplectic geometry when you have x and p. When I do geometric quantization, what's crucial is that after making the pre-quantum bundle, I then quantize, which then means I've got to restrict to a configuration space, which then means I impose a constraint similar to this, and then I only have functions of x, or functions of p, and of course they're related to a canonical transformation that preserves the symplectic form. So now I would have either x or x tilde, or in this case y or y tilde, and then, but then I've got the constraint, which means my functions will only depend on one or the other. Okay. So this connection with geometric quantization can be made a lot more detailed than I've done. So I will refer to you to papers by Weismann, who constructs this overall space as a para-Hermitian manifold, and then goes through the whole technology a la Weinstein of geometric quantization in terms of constructing Courant algebroids and so on. But then the thing to keep in the back of your head is that, yes, in order to have this, you need a structure. It's now ODD instead of symplectic structure. But it's not just that. You need a constraint, and that's like doing the quantization. I should add, I think there's then some more details. So when we do geometric quantization, we also have the notion of a metaplectic correction, that there can be phases given by how the measure changes when you take different choices. So when you look at that again here, I've not said how the measure will change when I do this. You'll get the dilaton transformation. And also, if you're very careful with the metaplectic idea, you'll get the phases that crop up when you get the e to the I pi over 4 type stuff in the partition function. But that's beyond this bit. Okay? Right. So, before we then move on to exceptional things, I want to make 2 statements. The first thing is, and I'm happy for people to give me their opinion. I have now told you that string theory is a theory of null waves in higher dimensions. And the tension is just basically the momentum going around x tilde. Yes, Jack.
I mean, what you're talking about is BPS strings, right?
Yeah.
I've
That's right.
turned off all the other oscillator modes, right? And just look at the BPS configuration.
Good. What you can do is I give you that solution. I can then look at the Goldstone modes of that solution, which would involve taking the solution, allowing the Goldstone modes to fluctuate in the background and come up with an equation and an action for those Goldstone modes. When you do that, you will get a string action. So it's like lots of brains. We find a solution in supergravity. That's fine. But then we do a Goldstone mode analysis that will give us dynamics of those brains. If I do this for this, and I have done it, it's in a paper from a few years ago with Felix Rudolph, that you take this action, this solution, identify the Goldstone modes, reinsert back into the action, the double field theory action, then you'll obtain, actually it's the Saitlin string action, which is this action where you've got left and right movers in one direction compared to the other. But it's a string action with oscillators. But that's what you'd expect from a brain. Yes, the brain may be strict, but you've got wiggles, which are part of the Goldstone modes. So now I'm going to tell you again. Is string theory a theory of massless objects in DFT? Because I've repeated this a few times, and I always expect people to say it can't be. Now, it has an attraction to it, which is the tension is not put in by hand. The tension is really related to the momentum in x tilde. So there's no mass scale. It's all massless. It's just coming from, I've got some spontaneous compactification of the x tildes, and then some momentum whose scale is then determined by that radius.
So in usual string theory, you have more than, I mean, the tension is just the tension. You don't have quantization, you have it in space.
Yeah, I mean, it's an interesting question. So there have been papers before where people have tried to quantize string tension and treat the string tension as a field, which is sort of what's happening here. But indeed, that's not what you normally do.
Now, I'm also a little bit confused. I thought this Q you were calculating,
Yeah.
which you then identified as tension, was the H field charge.
Yeah, it is. Yeah.
But of course, we know we have strings which have carry no B field charge, no H charge, and are perfectly fine strings.
Can I have that? Usual string theory. Because they're close strings. Yeah. So the overall. So
Your BPS
no, is infinitely less infinitely stretched. Yeah, yeah,
oscillations on that.
yeah.
That would close
Good.
the lines.
Yeah.
So how do
Yeah.
they fit in here?
Don't know. I didn't say I had the answer. I want the answer.
Don't have the
I don't have the answer. Okay. So, this would be where you've got the thing in a line infinitely stretched out. I don't know. I find it curious as a reinterpretation of a solution that we know, that we've done the Kaluza. I mean, the reason for going through this is that we've done the Kaluza-Klein lift, and then you're left with this question of how real are those extra dimensions when you're lifting? And so I'm trying to say to you, the things which you accept in string theory, the presence of magnetic charges, the presence of these solitonic type strings, which then have momentum in this direction, would infer that this is more than just adding a dimension and then saying, oh, there's no dependence of the fields in that direction. Okay. Let's,
One last technical question.
yeah.
So everything you're going to do is with the strong constraint?
Here, yeah. So it's, I mean, let me just make the statement then, for those who don't know. This, like this, is what's called the weak constraint. Choosing this or this is strong, right? So, have I got the wrong way around? No.
My understanding is that the difference is whether you impose this on everything
Yes, exactly.
or whether you impose it only on the fundamental.
Yeah. It works out to be sort of the same, in the sense that if I impose it on everything, then that implies this, really. So that's really how I think about it. Or you have this sort of quadratic operator, and I do not know how to make sense, which means just I don't know, of how to make sense of solving the theory subject to this. When we do this, we're just in Kaluza-Klein territory, and I know what I'm doing. And it's an open question in DFT, how do we reformulate the theory to really do this? Now, if we go back to string field theory, actually, then the origin of this is level matching. And this 0 will get replaced when we have oscillators by NL minus NR. So it's a bit like you've picked... There's something to be understood here. And I think this is one of the biggest holes in DFT, is that the formulation where we do this more generally, where we just solve this constraint, is not really understood, at least not by me. Yeah. Yeah. Yes.
So when one thinks of finding the diagnosis coming to conserving, you get to it through the time conditions. You're kind of looking at the section conditions.
Absolutely.
And then you miraculously hope that my theory somehow reconstruct the missing momentum of the solid section and introduce an operator.
Yeah.
Theory that might do that. Are you suggesting a similar scenario that there are quantum operators in the review theory that introduce power?
I think there's something I'm saying there's something interesting that I can find solitons of DFT that are strings. And then yeah, but I'm not sure what more I say after that, and that's the, because we've all the things we've discussed, but there's something there that looks well, that's what I'm saying. Yeah, well, yeah, exactly. Yeah. Yeah, so that's perhaps a good analogy, is that, of course, in geometric quantization, we could also do Moyal quantization, where we don't restrict fields to only depend on X. We can have fields depend on X and P, but then we have a star product. So then that will be a way of then somehow imposing this, is having a sort of star product. Now, technically, that doesn't work because of it's not a star product because that's a symmetric thing. But that would be some notion. You'd have a deformation quantization where you'd include both. Then you look at amplitudes and products of fields, and then the product would be deformed. And that would be a way to do this weak thing. But I don't know anyone who's done that. I know people who are looking. Okay. Okay? What time did I start, Christine? I've got 25 minutes. What am I going to say? Okay. So let me say a couple of things before I move on to EFT. So once you've constructed this trick of having 1s1 fibration where you've got the tilted direction that you're fibering over, once you've got that once, you can then look for more exotic type of brane solutions where you glue using the generalized Lie derivative, so your patching can be more exotic, meaning you're not just going to glue with diffeos, which is a subset of the generalized diffs, but glue in more elaborate ways. So we have a finite form for ODD. So this was written down by Barton and Hom. And you can certainly do it for the sort of twists that you might want to try. You can certainly do it in very specific cases. If you don't, it's maybe not the most general thing. And so what this leads to is that this allows an explicit construction of what go by the moniker of exotic branes. So exotic branes are not solutions of supergravity. They are locally solutions, but they have monodromies such that when you go around some closed one cycle, then you come back up to what people would describe as a T-duality. Okay? So double field theory is ideal for constructing this because we have as a local symmetry the generalized diff. So let me just do one advertisement with my student Rei Otsuki, who'll be looking for jobs relatively soon. We constructed a set of, in fact, a huge set of exotic branes just as solutions with patchings in generalized diffs, and then matched up to expected exotic brane solutions that Jan de Boer, Misaki Shigemori had from more general considerations in string theory. So this yet again goes, once you've got this sort of Kaluza-Klein prescription, you can then mess with the topology of how you're gluing the extended spaces. Only now, because I've not just got one dimension, I've got a whole D of them, I can get more and more interesting exotica. And especially since then my patching conditions can have more and more exotic things. So this is one way in which we then construct T-folds and other things. And there's a whole set of charges called the Q charge and R charge, which measure these things. If people know what Q and R charge are, then good. If not, I'm not going to define it for you. No, they can be for the exotic branes of Shigemori and de Boer. There are even more non-geometric ones which are worse, but the one with, say, Q-flux, which would be what's called the 522 of de Boer and Shigemori, that one, for example, that you can construct as a thing. And then you can get more and more away. Okay. Right. Okay. So let's move on to. So this was great. So back to theology. Somebody said that they were a great believer in string theory. I'm of the M theory generation, and I'm a great believer in M theory, and that one doesn't want to do things in 10 dimensions. One wants to do it in 11 dimensions, and you don't want 2 forms. You want 3 forms, right? So the next step is we go back, and we've answered this question now for the NS sector in, let's say, 10-dimensional supergravity. Only now you would say, what do you do in 11 dimensions, where we have, so in 11D, where we have a metric, and we have a 3 form, and potentially a dual 6 form. Okay, so you've now decided that we believe in this whole lifting program, and let me just see what we would want to do. So we want to combine G now with C3. Let me leave this out of the game for a bit. And so you can construct a generalized metric where you do a similar trick. Sigma, where you combine, and in now, something like this. So this is similar to what we had before with the B field, the off-diagonal bits, only now it turns out the thing we need here is the inverse metric squared. And actually, there's got to be some anti-symmetry that goes on, so it's like the metric on 2 forms. Now, you might ask, well, how many dimensions is this in? And this is where you can't give a very quick answer, because it depends on what it is you want to start with in the number of dimensions here. So let me not do 11. We don't want to turn it all the way up to 11 quite yet. So instead, yeah, my Spinal Tap friends joking in the front row. But let me just do D equals 4 as a concrete thing that we can look at. So this is going to be a 4 by 4 block. And this is actually going to be 6 by 6. And the reason why we've got these 2 forms is, if you remember how we did the construction before, we had the vector field of diffs, which would just give us v mu, but now the variation of c mu nu rho is going to be given by a 2 form. Okay? Chi nu rho, a 2 form. So now we need to add a 2 forms worth of dimensions in order that my generalized vector field will be able to capture the gauge transformations of a 3 form. Okay? Well, we get worse. We'll get there in a minute. It's worse. So at the moment, I've not got this 6 form because I'm just looking at D equals 4. So you can't have a 6 form in D equals 4. So let's just do one step at a time. So when I do this, I get 10 dimensions in total. And what you can then show is you can then follow through the whole thing again. You can work out a metric for, so there's the metric. You can work out an action for this thing that will reduce in the appropriate way. And so let me just write down here, D equals 4. And then I'm going to put here additional dimensions, total, and then rep of what group. So for D equals 4, I need 6 initial dimensions, 10 in total. This turns out to be the 10 of SL5. Okay, you can show it transforms as the 10 of SL5. So these things transform as SL5 over SO5 coset. As I go up, then I end up with 5, and then I end up with spin 5, 5. And then I keep on going. And D equals 6, something funky happens. I now need to include this one, so I jump. And now got to additional modes with that. And then, oh God, I can't do it off the top of my head. More things happen, and we end up with a rep of E6. It's 27, it will be total. So, okay, whatever it is. 21, thank you. And I think you get the 1 from one more thing in there, and then you get the others that go through. And then we keep on going. Yeah, oh, sorry. Yeah, that's right, absolutely. Yeah. Let me just here that we will get rep of E7, rep of E8, from essentially filling out this thing whereby we add in the appropriate fields, and here I'm also missing the fact we need an additional thing corresponding to the Kaluza-Klein monopole, which gives us a mixed tensor, and then we keep on going. Now, some people will want to keep on going some more, and so Martin, you're going to talk about this today? No? Never mind. He's written many good papers on it, on how you can extend this to E9, when I think of E9 as an affine E8. And then some of our colleagues got to E10 and E11. Now, for me, okay, I personally stopped here because it got big. But what I wanted to bring out is this structure, which is very much like Kaluza-Klein, with this set of constraints. And what I've not mentioned is then you can ask me, well, what is the generalized Lie derivative? And what then are the geometric structures in this theory? So the nice thing is that once you've got this idea of what the generalized Lie derivative is in terms of the y tensor, so let me just write that back up, is the generalized Lie is the same in the sense that there is just one single deformation and let me say this is true for ED D less than or equal to 7. For E8 and beyond, one needs to do things a little bit more sophisticatedly. But what this y tensor is the y tensor will be a different invariance of these groups that you work out. Okay? So let me give you some flavor. So we work out that the size of the space forms a representation of these groups, and the generalized Lie derivative has this y tensor which says how I deform the theory, and that is also given in terms of invariance of the group. Okay? Yeah.
Why in C6 is an 11-dimensional thing?
Yeah, yeah.
C6 in other dimensions?
Okay. So then what one needs to do is, you need to do this properly. What that means is, I first break up the 11-dimensional theory into 4 plus 7, and then extend, and then the fields will then break up where I will have, I won't have C6 at that point, but start in 11 with C6, democratic formulation, drop down under the reduction, yeah, completely naive, then take the field, and then basically keep everything, but then I'll have some indices which will be associated to the 4-dimensional ones, and then you augment the 4-dimensional space like this, and then you've got the whole theory with all of the things together, and then that will include some bits that will be mixed indices, which are the sort of things that you thought I was throwing away. And that's what goes under the name of exceptional field theory, as developed by Hommans, Samtleben, so with Malcolm and I, we did just this internal part. Samtleben said, how do you get all the off-diagonal bits and keep everything that's got the memory of 11 dimensions? Yeah.
So, in the big four case, you have the C. How do I
I mean, you can do all sorts of games like that. I'm not saying you can't.
What happens if then you add 4 additional dimensions, not 6?
Well, you want to generalize it into one topic. You really want to generalize the curvature. So it would be just a 0 to 1. It's just, I mean,
See,
four
yeah.
dimensions, C3 has no dynamic.
Yeah, exactly.
Logical constant.
Yeah.
That's if you know the answer.
Yeah. There are ways. Let me not answer that. You can think about it, and I don't think you come to any deep conclusions after you've messed about. People have done things like that, but there's a. Well, okay.
You sort of answered that by my answering my question.
Yeah, exactly. Because then you just get the fields as you split up.
Really, you know,
Yeah, exactly. Okay. So then what happens is, okay, so we have this, and then the same thing happens, only now the constraint is given in terms of the Y tensor. And now this doesn't halve your space to solve it. This takes you back onto the physical M-theory section where you recover 11 dimensions. But there's an alternative solution, and then you'll actually end up having to lose an extra dimension, and you'll be back onto 10. And that, of course, will be associated to 2B description. So this is something which, if you like, we know happens in M-theory because the extended objects in M-theory, the membranes, have 2 dimensions. If you're swapping a winding and a momentum, you don't preserve the number of dimensions. Okay? And that's why the different choices of section of this equation end up actually having one dimension bigger than another. And then again, this can form the usual business that there is, it doesn't, well, this comes from it not closing. What's not obvious in this, but is what you need to go through, is that there's a lot of reducibility. So then, of course, this is related to the reducibility of this gauge field. And then, well, there's a very interesting gauge structure, which can be the origin of actually an L-infinity algebra. Is Martin going to talk about that? And Martin will talk about that. This, good? Okay. So then finally, you just keep on going. You've now all learned what you do next. You can construct the membrane as a momentum mode. You can construct the M-theory fibrane, Neil's favorite object, as a Kaluza-Klein monopole, twisted now with the Y tildes. And actually, if you do that, you can then also look at the Goldstone modes of that, and the self-duality constraint on the fibrane is then related to this choice of section condition, the fact you have an additional projection. And then, again, look for more exotic states, because now we're gluing with the full ED group, and so we can get even more exotic branes than before, and all of a sudden, the spectrum of string theory blows up, where we've got all these exotica. Okay. People may want lunch. So, you know, let me end there with the simple statement that, you know, DFT had its origin in closed string field theory and a truncation. It was mysterious to me what the truncation was. And then there was all this mathematical structure behind it. What I've tried to tell you here is that there is a very simple picture, which is I give you an action, and I say to you, combine it into one geometric thing. You realize very quickly it cannot be usual Riemannian geometry. I must have an additional structure that's preserved and a constraint. I then force myself to solve the constraint, but I am not back down to ordinary supergravity because I can do global twistings, and I allow myself to have momenta in those directions which will correspond to charges in the system. which from the supergravity point of view would be like having delta function sources. But here, this comes from having momenta. I don't know what we do more, but somehow it feels that there is still some things to run, because it allows us a very different way of looking at string theory and M theory. And there's a whole bunch of things that people can look at now in terms of truly non-geometric solutions, in terms of smoothing out singularities, et cetera, et cetera. Thank you very much.
So in the end, DFT consistent quantum field theory is differential field theory? What is it?
Good. It's as consistent as a quantum field theory as Einstein gravity. Now, but that's a serious problem. So then, because what have I said? I mean, I've written down a two-derivative term with some fields, and I mean, in D equals 10, it could be, right? I mean, how can this be renormalizable? It can't be any better, right?
It can't be any better than the Kaluza-Klein.
It can't be any better, right? So I don't think I'm sorting that way. The one thing that I find a bit curious, well, let me not say anything contentious. So we do need string theory still, because we need to make it ultravioletly complete. But then what I've done is organize it in a different way, especially by the time I've gone into this M theory thing here. I've reorganized everything into representations of U-duality and all this sort of stuff. So, but no, it can't be, it can't be any better than usual gravity in D dimensions.
It makes sense as a classical field theory?
It definitely makes sense as a classical field theory, because I write it down and then I find solutions, classical solutions, and then I can identify them with states in the string theory. But you might be able to do a little bit better. I mean, half BPS type better, if you see what I mean by that. Yeah. Now, I've not done that, but people have started to look at black holes in this. And as you well know, black hole entropy formulae are U-duality invariant. So when you have the descriptions in terms of EFT, then the natural ED invariant things that come up in entropy is there as part of the geometry. But I don't think that's been looked at sufficiently, actually. Yeah. Yeah. I so wish I knew. That would be so interesting. So there has been some work by Dieter Lust and others, maybe Richard Szabo's in that as well, where they tried to look at that, and they found weird things like the phase space wasn't even, which confused me a lot. So I don't know what the status is. Yeah, I don't know.
How much of this can be generalized to high-derivative connections?
So indeed, by Diego Marquez and the group in Argentina, and then also Barton with Olaf, both those sets of people have done, actually Warren, I think, have done the next higher derivative corrections, meaning R squared. And there's a sort of conflict in the sense that you can choose to have manifest ODD or manifest Lorentz, but not both at the same time. Yeah, but you see, the automorphic forms are so natural in this, right? Because that's just summing over momentum states in the exceptional space, and you'll get those automorphic forms. And indeed, there's a very nice calculation. So there's a question about how quantum is this. I should have said this. There's Axel Kleinschmidt and Guillaume Bossard did a calculation where they did a one-loop thing, one-loop diagram. And they basically summed over all the momentum states in the full exceptional space. And then what you reproduce is exactly these sort of automorphic forms that Michael Green and others had for the things that control high derivative corrections. And then that was at half BPS, because some of these things are half BPS, the things that correct. The thing at quarter BPS is even more interesting, and there's interesting cancellations. So actually, in that sense, you can do quantum things. And you get these automorphic bang on. You're not summing over state, you just sum over the momentum modes, and this constraint, this is actually, when I replace these with P, is exactly the half BPS constraint. So if you're familiar with all automorphic forms, you sum over all momenta subject to a constraint. It's the same one.
In some sense, the actually that calculation shows that weak constraint is automorphic.
Yeah.
You have weak constraint in everyone.
Yeah, absolutely. Yeah.
Necessarily global.
Yeah.
Yeah,
Yeah, no, exactly. So when you go around in the loop, you just apply the weak, which is in terms of momenta, and so you just have it obeyed at each vertex, and then yeah, they get this amazing result. Which I guess it had to be true, but it's really nice to see it. Oh, so it's yeah. Only look, it's the same. But it's just this simple thing that you would do the automorphic form. You'd sum over charges, right? You worked on this at some point. You sum over charges. So that now all that happens is charges become momenta. So as I sum over double momenta, or ED valued momenta, so I have PI will be a usual P mu, and then it would essentially be things that will be corresponding to the M2 brane central charge, the phi brane central charge, and so this would be momenta with 2 indices, momenta with 5 indices. When you sum over all this momenta, which is in some rep of ED, you're summing over states with momenta and membrane central charge, phi brane central charge, and that's exactly what you do to construct the ED invariant forms. Of course, the form's the same. The form is the form. The thing that's nice is that there is an ambiguity of which form you take. If you just say you want an automorphic form, you might say what representation of ED. And what this does is tell you what the representation of ED is and what the constraint is, because the rep is just given by this momenta and the constraint is given by that constraint. And then you just sum. And then you go to the literature and there's, I think, Epstein and so on, and then you find it's bang on there.